Okay, let's talk about the MVT for integrals, the mean value theorem for integrals. Now, if you remember, there was one for derivatives. It said essentially the a rock equals the I rock at least once on a closed interval as long as the function was continuous and differentiable. Continuity implied the differentiability as well. It was the one where we drew this and said, well, right there and right there, the slope of the tangent line was equivalent to the slope of the secant line. So MVT for integrals, not directly related, I'd say, but there is some similarity. So the mean value theorem for integrals. Let's set it up with this. This graph here is the shaded part is the area under the curve from 0 to 2. The question they pose here, is there a rectangle with the same base from 0 to 2? So that would be a base of 2. That would vary from each question, but in each function. But from 0 to 2, based on the interval, whose area is exactly equal to the value of the definite integral. So is there a rectangle that has the exact same area as the area under the curve? Okay, that's this. Here, this one is certainly less than the area under the curve. This rectangle is definitely bigger. It goes outside too much, way more than the other one. And this one, what they've done is they found a c value, some x-coordinate, and the height, f of c. And it appears that this c value, the area of that rectangle that would be formed, has the same area as the area under the curve. If we flip to the next page, that is what the MVT for integrals basically says. Okay. Maybe I'll discuss first. You need the mean or the average value your function takes on, as illustrated up here. Here's the average value of that function, the average y value. You're going to need that to help you out. And what it is the integral, the area under the curve of f of x from a to b. It's 1 over b minus a, though. So 1 over this distance. And if you do that times the area under the curve, that'll give you the average value. So this would be the average, as I said, or mean y value or height of the graph. Now the mean value theorem for definite integrals, or just for integrals, is this. Continuous closed interval, as normal. If so, this is, like the MVT for derivatives said, if you have a continuous function on a closed interval, there is at least one, it's guaranteed at least one number, at least one spot where the a rock equals the I rock. This one says if you have a continuous function on a closed interval, and there exists at least a number c, at least one c value in that interval, such that this is true. Now, or equivalently, you can divide by b minus a on both sides to get this form. So if I took this one over here and divided by b minus a on both sides, we would get this, just putting the b minus a with a 1 on top out front. Okay, so they're equivalent. Now, sometimes this one in red is used a little more. I think conceptually, though, the green one makes a little more sense. Here's why. I'm going to this one right here. This is the rectangle. The left side of the equation is the rectangle. Okay, out the area of the rectangle. So b minus a, that's the base of the rectangle. You know, here's a and here's b. That's the base of the rectangle. F of c, so it's some c value on this interval. F of c is the height of the rectangle. So that's base times height for the rectangle. Again, f of c is really the height. B minus a is base, length times width, whatever you want to call it. So that's the area of the rectangle, as I said here. But the other one, we'll put it in blue here. Well, we know that one. That's the area of the curve. So here, that's whatever. This area of the curve. So really, I think this is the best form. This one just says the area of the rectangle, left side, equals the right side area under the curve. Area of rectangle equals area under the curve. That's what I said here. And so what we can do, we can use either form of it. The other one I'll put in black up here. Either form. And we can use, again, the right side of this equation when you divide by b minus a is the average value. And so to find a C value, kind of like we did with AROC, MVT for integrals before, AROC to IROC, we can find a C value that satisfies the mean value theorem, where this would occur. Basically, that's what we did for MVT for derivatives. So let's try one. First of all, find the average value of the function on the interval. So here's our function down here. Here's our A and B. Now, if you'd like on this one, really the average value is the right side of this equation. It's this one, this whole thing. What I like to do, though, sometimes is just do the area under the curve, right, and then divide by b minus a. So what I'm going to do is just the integral from a to b, -6 to -3, of f of x. And by the way, you could already have the 1 over b minus a out there. I'm just showing you how I kind of like to do this one first. Okay, so let's see here. I do capital F of x is my antiderivative. That's going to be the -x cubed over 3. Then we got minus 4x squared and minus 17x. We're going to do f of b, -3, minus f of a, -6. Okay, I'm going to put in -3. Now I'm putting it in into all these x's and getting a number. I got 9 minus 36 plus 51 is 24. So I did them each separately, but you could also just put it in the calculator all at once. Put in y equals, look at the table, any of those are fine. So I get number 24 minus, I now plug in -6 in all of these, and I get 30. And so we get -6. Now that right there is purely what we've done before, the area FTC1, area under the curve. I should have mentioned that, yeah. We did FTC1 here to start. That's the area under the curve. And I get the average value. You'll notice the average value, well, it needs a 1 over b minus a in front. So 1 over b, -3, minus a, -6, and then times whatever we got there. Okay, the integral from -6 to -3, which we just did. We just did all of this, and we got -6. Let's reduce this one. -3 plus 6 is going to be 3. So we get 1/3 of -6, which is -2. So that's the average y value on the interval for the function. That answers part A. Now part B, find the value of C that satisfies the mean value theorem for integrals, value or values. This one basically, I usually like to take it back to here, okay, the original one. Set the area under the curve equal to the function f of c times b minus a. Now, equivalently, since we did this form, we already have the average value. We can just set it equal to f of c. Here, I set it down here too. So now, let me say, here's what I'm doing in part B. I'm setting f of c equal to the average value. And the average value from part A is -2. F of c is the function with c plugged in. F, little f, not capital F, just the original function. So we're finding, think about it, we're finding where the original function, it has its average value. We're setting the average value equal to the original function, finding out where that occurs. Okay. Let's go ahead and solve this, and I'll tell you one other option we could do in this. So I'm going to get everything to the right side. I'm adding c squared, I'm adding 8c, and I'm adding 17, so we get plus 15. Then I'm going to factor, and we got plus 5 and plus 3. So we get -5 and negative 3. There can't be more than 1. There can't be more than 1. So think about that like this up here. Basically we found this is like C1 and C2. These are the C values. We just found where the function takes on its average y value. That's what we just found. Okay. Now, one last thought here. If you were just asked part B, okay, I set it up so we found part A first to help us out. I would go back. Let's go down here. I would go back to that first, that first one above, f of c times b minus a. Okay, well, the left side there is the area of the rectangle. I think this is the easiest one to remember. The right side is the area under the curve. So you can always go back and set these equal and start from there if you'd like. All right, so area under the curve, that was the one where we got negative 6 from above. F of c is the original function c, what was c plugged in. And then b minus a, that's where you could just do b minus a, negative 3 minus a negative 6, and you get 3. So area of the rectangle on the left, area under the curve on the right. And what happens here is then you could just divide both sides by 3, and you would then be right back here. So I'm showing you another way you could have gotten to this setup. So if you have the average y value, just set it equal to your function. If you don't, if you're starting from scratch, just do the rectangle area. This is a good way to do it. You could also find the average value first. Or just do the rectangle area, area under the curve, divide by whatever number's here, and you'll be set up and good to go.